analyst at PhonePe and has over 9 years of experience of the industry applying machine learning models in the digital advertisement domain and currently in the fintech domain. So over to you, Shiladit. The virtual stage is all yours.
Yeah. Am I audible? I think the participants can hear me. Atrij, can you confirm if I'm audible?
Yeah.
I'm unable to share my screen.
Just a second, just a second.
Yeah.
Will you try now, please?
Yeah. Is my screen visible?
Yeah, it's visible.
Do I need to start the video or how is it? Hello? Hello? I'm unable to hear your voice. Hello?
Hey, can you hear me?
Yeah, I can hear you now.
Yeah, you're audible. Completely fine.
Okay. Should I start my video? Or this is fine.
Whatever suits you.
Okay. Then I can just start with the session, I guess. Yeah. So hello everyone. Please, Atrij, just let me know if I'm not audible anytime midway. Yeah. Okay. So hello everyone. I'm Shiladitya. Currently, I'm working as a data scientist for PhonePe. And in today's session, I plan to give you a broad overview of what interpretable AI is. So if you look around resources in the internet, you'll find different terms such as interpretable ML, explainable AI, but they all basically constitute a set of methods. And the plan for this session is to kind of walk you through the basics of each of these methods, right? So first, let's try and understand that why do we require interpretable AI at all? The way the entire machine learning pipeline works is that we capture certain data and to basically predict or to understand patterns in the data, we build some kind of model. Now, many a times, due to business needs, we need to understand the underlying process or at least make other stakeholders understand what the model is exactly doing. So the three main reasons, I guess, why interpretable AI is so important is one is to understand the underlying process, because if we get hold of what is exactly happening underneath, that's a big benefit to any business. Second is to build trust with the model. So if say a model is performing very well, but we need to make sure that the model is performing well for the right reasons, right? There is no basically garbage data going in because of which the model just happens to perform well for the time being. And on similar lines, it basically helps us understand the reliability and stability of the model. So if we understand which features are important in the prediction, we can take a guess of how long this model will be stable with respect to time, so that if any feature which may change in the future, we can change our model appropriately then, right? So how do we go about doing this? If you see the chart on the left, which is basically explains the trade-off between the predictive power of a model and the explainability. You see the cluster at the right bottom, and those basically constitute methods which are explainable on their own, simple to understand, but you always have a trade-off with the predictive power or the accuracy, right? So one way is to build interpretable models. So if you are pretty sure that your the process that you're trying to model is not that complex, then the easiest way out is to choose one of these models and go ahead. And the weights of the models, or say the splits made by the decision tree, that would kind of give us insight as to what the model has learned, right? But with the progress in the field of deep learning, and also boosted trees, right? I mean, these days we use XGBoost just out of the box to solve any kind of problem. Um, we try and use extremely complex nonlinear methods, which may not be easily interpretable right from the output, right? So, in order to handle these, let's have a look at what all methods are currently available to explain the black box models that we build. So before we go into the methods, it's very important to ask the right question, right? And asking the right question, or the question, basically will govern what kind of method we choose to interpret our model. So one of the methods, I'll just skip a slide and go ahead, is one of the question rather that we ask is, how does model prediction vary with respect to the features of interest, right? So any model that is built, and if you just get me the model, I would want to know how this model varies with each of the features that have been put into the model. That would definitely help us gain some understanding of how the model performs, right? And in order to answer these questions, this is basically a global question. We are not looking at an individual prediction and trying to dig deep further. We are trying to understand the model as a whole, right? So for this particular question, we resort to global methods. And the model agnostic term is, we would like to use methods which do not depend on the type of the model that we build. So we would be looking at more generic kind of explainable methods, which would work for any model that we have built. And this is a layer on top that we can apply so that we understand what is going on inside the black box model, right? So coming back to the previous slide, that becomes a global model agnostic methods. Another set of methods can be classified as local model agnostic methods. So this basically gives us the significance of instant features for prediction. So it means that for each prediction, we try and understand which feature is playing an important role in the prediction of only that particular instance. And local model agnostic methods, if you basically average them out across all instances, we do get a global view also, right? So these are the two broad kind of methods that we will be looking at today. And I will come to example based and attribution based later. These are just another subcategory of the methods that we will look at. But the main two methods are the global and the local model agnostic methods, right? So coming to the global model agnostic methods, as I mentioned, it basically answers on a whole how the model prediction varies with respect to the features of interest, right? So the first method that we look at is a set of plots called a partial dependence plots. Now, as the name says, we basically have the feature on the x-axis and the predicted value on the y-axis, right? So the partial dependence plot will basically take for each feature value what is the average predicted value given as an output by the model, right? So let's have a look at how to kind of chart these partial dependence plots for our models that we build, right? Uh, My screen hopefully is visible. Just let me know if you can't see the Jupyter notebook. Okay. So for the partial dependence plot, the data set that we'll be looking at, so this is a publicly available data set. It's the bike rentals data set, right? And the goal of this data set is to predict how many bikes will be rented depending on features that basically qualify the weather and the day um, uh, of the date, basically, right? And this is available from the UCI machine learning repository. So this is publicly available. So let's start running this notebook and see how to chart the partial dependence plots, right? So here we read the data frame. So you can see that for each row, you basically have different features like holiday, weekday, temperature, humidity, wind speed, and the variable that we're trying to predict is the count, right? So you see here 985 bikes. So basically for that month, for that particular date, 985 bikes were rented. And just to give a context of what this is, like you would possibly rent a vehicle if the temperature is very hot and going outside is kind of a trouble, right? So that's what the model should basically be saying. So there are 731 instances in the data frame, right? And we build a simple kind of just do the normal train test split, and let's build a model and see the output, right? So the model building is not the main focus of the session. So I'll just run through these cells quickly. And we are using a package called Alibi. I will come to this later. But this is like an excellent library which has kind of collected and still developing all these interpretable methods under one roof, right? So we are going to use the partial dependence plot from this package called Alibi. Partial dependence plots are also available as part of scikit-learn. So we'll see that later in an example that I'll show towards the end, right? So here we just make a copy and do some check. Let me just. Yeah. Yeah, so you can see we have a random forest regressor that we have built. So we are predicting the number of bikes. So we are using a regressor. So there's some amount of maybe overfitting happening, but we are not too bothered about it. Currently, the train score is at 0.98 and the test score at 0.9. So let's go ahead and plot the partial dependence plots. So if you see, this is the API that we are calling from the Alibi package. And what it takes as input is a predictor. So you can basically have any kind of model, and you just need to write a predictor function which will give the output from the model. So this could even be a set of rules potentially that you have kind of handcrafted and just written a logic to predict some kind of output. So as long as the function gives a certain output, certain probability, or in this case, say a certain number, it's fine, right? And we give the feature names, the target names, and the categorical variables. So yeah. So the first thing in partial dependence plot is you would see this parameter called kind, and here we basically have given average as the kind. So I will come to this later as to why this is average. But let's plot the explanations first. Right. So this is the entire data that we receive after running the partial dependence explainer. And if we look into the JSON, right? So we have this key called data, where you see a list of arrays here, and the feature names here. We are basically trying to draw the partial dependence plots for 4 features, which is temperature, humidity, wind speed, and the season, right? So if we look at what these values are, right, the like we are querying the data key from the explainer output. So you would see that there are basically 4 elements in this list, right, which I've highlighted just now. So the 4 arrays that are present in the list, they correspond to each of the features that we have given as input, right, for which we want the partial dependence plot. Now, if we see the size of the array, you would see that each of the variables, the array corresponding to each of the variables have 100 elements in it. And if we go slightly on the top, there is something called a grid resolution equal to 100, right? So let's take a break here from the Jupyter notebook and see what exactly is going on and how do we actually plot the partial dependence plots, right? So I'll just pull out an Excel sheet. So I hope the Excel sheet is visible. If not, please let me know. Right. So what exactly is the partial dependence plot? So say we have a data set, right? You can see the data set at the top here. It contains of 3 features. Okay. And the model basically outputs this particular target, right? So here we have 3 rows with 3 different values for each of the features and 3 different predictions given out by the model. Now, in order to now what do we mean by the partial dependence plot is that we want to know the average model behavior with respect to one of the features, right? So say we select feature 1 and we want to draw the partial dependence plot for feature 1. On the x-axis, if you see these cells here, on the x-axis, you would basically have the values of feature 1. And on the y-axis, you would have the average model output. Now, what do we mean by average model output? Is basically while finding out the partial dependence plot, what it does internally is for each of the instances that are present in your data set, it will randomly or basically try out all possible values of the feature that you're trying to find the partial dependence plot for, right? So if I basically mask the feature F1 for now, you see that our data set has 3 different data points comprising of F2 and F3, which is basically B1, C1, B2, C2, and B3, C3, right? So now for finding out the partial dependence plot for feature F1, for A1, we will try out all possible combinations of the rest of the data set. So for A1, we would also append B1, C1. For A1, we would also create B2, C2. And with A1, we would also append B3, C3. In this way, another permuted data set is created internally, right? So for every instance, we basically try out all the possible values of the feature F1. So we have 3 rows for A1, another 3 rows for A2, and another 3 rows for A3. And then we basically take out the average, we group by this feature, and we take out the average of, say, that the model output, and we get one point of the graph. So if I take the average of y11, y12, y13, I will get y1 mean. Similarly, if I take this average, I would get y2 mean. And if I take this average, I get y3 mean. This basically, in words, if I had to put in plain English words, it says that when the feature F1 takes the value A1, on an average, the model outputs y1 mean. Similarly, when the feature F1 takes the value A2, on an average, it outputs Y to me. So in this way, this is a dummy example, and hence we just have three distinct values. But say we take a continuous feature, it would have maybe thousands of different values. And for each of the 1,000 values, we would find the average model prediction in this way, right? Now, there are a couple of problems that we can see immediately is that if our data set size is very large, and if we have a continuous feature which has 1,000 unique values, the permuted data set that it's creating or the intermediate data set that it's creating would explode, right? Because it would have 1,000 into the size of the data set values, right? Hence, in order to get around it, the first thing that it does internally is obviously it doesn't try out all the values. It basically finds deciles or say percentiles and tries out certain values for the continuous feature. Okay. And the grid size parameter that we basically saw here basically controls how many points of each feature do we really want to sample, right? So once we sample here 100 points, we will get the average model prediction at each of those 100 points and plot them. So let's just go ahead and plot them first. Right. Yeah. So here along the x-axis, this is, let me just zoom in a bit. Yeah. So the first plot is for temperature, and you can see that the predicted number of bikes increases till the temperature is say around 25 degrees Celsius, and it then kind of starts decreasing. And for humidity, initially the model prediction or the average model prediction is kind of flat, but at around say 55, 60, it starts tapering off. And wind speed, like if we see the scale, it doesn't have much. It has a very slow decline, and it kind of starts tapering off at 25. So these plots kind of give us a sense of, on an average, how the model prediction varies with each of the features. Similarly, this is a categorical variable. So it kind of, for each value of the categorical variable, it gives us the average prediction of the number of bikes, right? So coming back to the Excel, so one problem which we saw is that the intermediate data set could explode, but that can easily be solved by just sampling not all the possible values, but just 100 of the possible values in the data set, right? But there's another main problem is that when it starts substituting all possible values, or at least the entire range of a feature for every possible value of F2 and F3, there is a possibility that it may start creating unrealistic instances, right? So for example, let's take a cricketing example, right? So where we'll come to this example later, where we'll try and analyze a cricket data set. But say we are trying to predict the probability of win, and we have number of balls bowled, right? Runs scored till now, say, right? Runs scored, and say something like wickets, right? These are the main three features that will be present. And say runs scored, it's a T20 match, say 140. Now, balls bowled, say, are basically 12 overs have gone, so say 72, and 5 wickets have fallen, right? Now, balls bowled will have values such as 4, 10, right? It will have 120 when the innings ends. So it will have a entire range of values from 0 to 120. Now, with PDP, such a simple kind of plot, what it will start doing is that for this combination of runs scored and wickets, it will also create another permuted data point having runs scored as 140, wickets scored as 5, and balls bowled as 4, right? Now, this basically is an impossible data point to get, correct? but PDP doesn't really care. It treats each and every feature as independent. And that is one main problem with PDP. So the main assumption is that it treats the features as independent and hence starts permitting all possible combinations. So let's see how this handicap is basically handled. But these are some of the insights that we can draw from the PDP plots for now. And then let's come to another problem that the PDP plot has, is that it may happen that in one half of the feature behaves a certain way with the prediction. So say, like, let's take this entire block. Say for first half of feature one, or say this value of A1, the target is basically negative, and for B3 and C3, the target becomes positive, right? And let's say that this keeps happening for every value of feature one, which is for A1, A2, and A3. So the mean of all the targets would be hovering around 0, right? But the actual reality is not that. There are some data points which have negative correlation, some data points which have positive correlation. And if we take the average, we obviously basically miss out on those patterns. So that can be handled by basically superimposing another set of plots called the individual conditional expectation, right? So let's not get much into the names, but if we just think logically, it will basically start plotting. It will not aggregate and basically give us a plot for each of these lines or each of these data points that we have collected, right? So why to average out and give? It will give us a sense of how each of the data point varies with the feature value, and how the model output varies, right? So just to have a look of how the uh, individual conditional expectation plots look like, right? So you have this orange line, which is basically the PDP plot. And this is the average of all these lines that you are seeing here, right? So this is for temperature, humidity, wind speed, and this is for season, right? Now there's a small slight adjustment that we can make to these ICE plots or ICE plots, is that if you see for season, because all the, like, a certain prediction can start from a larger value, the small variations are basically lost in the visualization. So what is usually done, like even if you see for temperature, because each of the points would start from a different prediction, right? So say the topmost line is starting from 3,500 and the bottommost is starting from 1,000, right? But what we care about is how much does this vary along the feature, along the x-axis. So it is better to subtract this value from the entire curve and then view the curve. So it will be basically a zero-centered curve, but it will show us the variations that are happening across different data points, correct? So I've already run these plots. So just in the interest of time, I'll just show them. So if you see here, once we zero center it, the variations are much more clear, right? So if you look at temperature, um, though, like, we see the temperature or the number of bikes increasing till say 25 degree and tapering off. For some of the data points, it doesn't taper off, right? For some of the values. Similarly, for here, there are values for which, so on an average, it looks like the highest is in fall and the lowest is in winter. But there are values where all the predicted output for each of the 3 seasons is constant, correct? So the PDP plus ICE plots together, they at least give us a good initial good sense of how the model is behaving at an overall level, at a high level, right? So just to summarize, the PDP plot is a very simple plot. It has the feature value on the x-axis and the average model prediction. The ICE plots are nothing but they are the disaggregated plots. So we don't take the average. We will plot each of the y11, y12, y13. And here, like basically, a curve would be formed from y11, y21, y31, right? And we see the variation of the model prediction with each of the feature value for each of the instances, correct? So these two plots together give us a good starting point of how to view or how to basically get an insight of how the model is behaving. But one major lacunae of both these plots is the correlation that has not yet been handled, right? So if two features are correlated, these basically still substitute the feature not taking into consideration its relation with other features. So now that is solved by, let me just get back to the slide. So we have looked at partial dependence plots. Then basically to solve the problem of averaging out and to just see like how the interactions affects each feature variation with the model output. The IC plots kind of solves it to some extent. But as we saw here, the shortcomings of PDP basically lies in its augmentation of the data set with every possible combination of the feature for each and every instance, right? So that is a PDP estimation on the left. Now, one obvious way, the next most logical step would be that don't permute or don't fill in all the permutations of the data point for all the instances. Just fill in or permute the points which are similar to the point under consideration, right? So say we go back to our Excel, and if we have B1, C1 and A1, B1, C1, we will basically try and permute only the instances in the neighborhood of that point and get an average across them, correct? But this does give a slightly better output or a better curve and better representation because it's basically averaging now on the conditional distribution, but it still doesn't solve the main problem of correlation because if there are two features which are correlated, then we would still get the model output to be the same. Like if the correlated feature exists, it won't cancel out the contribution by the correlated feature, right? So in order to solve this, there's something called as accumulated local effects plot. Now what this does is, instead of trying to find out the average model prediction behavior for each feature value, it basically tries to approximate the difference in prediction across small intervals of the feature. Okay, so if you see on the x-axis, let's assume that we have this feature one on the x-axis, right? So what it will do is basically it will bin the feature into some n buckets, and now for each of these sections it will take all the points, right? So say it will take all these points lie in one interval, and it will augment the value of feature one with the starting point and the end point of this interval. Okay, and what it will try and do is try to find out the difference in the average prediction when starting point was imputed and when the end point was imputed. So what will happen if there is a correlated feature which also affects the model prediction? The model prediction won't change even if you augment it slightly with different values, and hence you will get basically a value very close to zero, as opposed to a PD or a modified PDP plot or the M plot, which we saw in this right hand side, which would give you a good model output value, right? So here it basically works on differences between the prediction if the end of the interval value was given and as opposed to the start of the interval value. And what it does, it basically accumulates these differences. It starts taking the cumulative difference across the entire range, and that plot gives us a sense of how the model output varies with the feature value, right? So this is just wanted to introduce these three curves because these are used like in many places, and one should, I think, just be aware of what are the lacuna of the PDP plots and why ALE plots are used, right? So just going back to the notebook and continuing. So here PDP plots, now just to end the global methods with the pros and cons. So the PDP plots, we can also have multiple feature PDP plots, and obviously we cannot have more than two because otherwise we will not be able to visualize. But if you see something like wind speed and temperature, right? So this is actually a very interesting PDP plot because it shows that when the temperature is between -5 and say 3 or 4, wind speed doesn't play much of a part in the prediction, right? Whereas if you see the green region up here above the yellow region, that shows that once the wind speeds go above a 20 or a 25, the temperature value, irrespective of the temperature value, if the wind speed is too rough, people don't go out and rent bikes. Okay, so there are these interesting insights which can be drawn uh, from a combination of features or the PDP plots which are drawn on a combination of features. And these are three variants, like the alibi package or the API of partial dependence plots and the alibi package. They can handle all possibilities of combination of features. So here we are seeing two continuous features being plotted. Here one feature is continuous and the other feature is, oh sorry, these two are two categorical features, and here one feature is continuous whereas the other is categorical, right? So PDP plots can handle categorical feature with ease because as we saw, it is nothing but it's just averaging the model output, right? As opposed to ALE plots, um, with ALE plots, what we saw is that it relies on creating these intervals, taking the difference and then accumulating. Now, the main problem is that when it accumulates, there is a certain order that needs to be maintained. We can't be accumulating in any order, right? I mean, so for a continuous feature, the order is obvious, but for categorical features, it becomes an issue as to what is like what difference should we be taking, right? Because the ALE or the local effect is the difference between when the end point of the interval and the starting point of the interval is considered. So ALE for categorical values is kind of tricky, not very well defined, and that is one big lacuna of ALE values, right? So here we see the ALE values plotted for the same features, and you would see these small variations or small jumps, and these are basically the intervals that have been created and the local effects being added up, right? So yeah, so just coming to the pros and cons, you can see the ALE plots, they're easy to visualize and understand, and they can definitely handle correlations. They don't struggle with dependencies, but ALE of categorical values is not well defined. And whereas for PDP and ICE plots together, they have like a very fast implementation or relatively fast implementation in scikit-learn, and it's very easily can be plotted for categorical variables, but as we saw, it struggles with dependencies. So that kind of briefly ends our overview of these global methods. And just to remind you, it's basically trying to answer this question: is the how does the model output or the prediction vary with respect to features of interest? Now coming to the next set of methods, which is basically the local methods, right? And this is answering the question that how much does each feature contribute to every model prediction or every instance of model prediction, right? So here, if you would have already read about it, there are two main methods, and mainly now dominated by one, but the two main methods are LIME and SHAP, right? So just to give a brief view of what the LIME method is, so I'll cover LIME and SHAP together and then kind of go to the notebook. So LIME basically stands for Local Interpretable Model Agnostic Explanations. So LIME actually has a big advantage that we will see later. But let's first try and understand how it roughly works, right? So now we are trying to find local interpretations or local explanations as opposed to the PDP plots and the ALE plots, where we were trying to just kind of have a broad overview of what the model is doing. So say this red cross, right, that you see on the graph is the point of interest or the instance for which you want a local explanation. So this is just one point in your data set. So what LIME does is that it permutes, it like takes small delta of this observation, and you could take as many as you want. So say you take n permutations, or uh, you take n permutations of this observation, then you kind of calculate the distance or calculate how far these permutations are from the original point. So you can, what you see here is basically a contour plot. So the blue region belongs to one class and the light orange region belongs to another class, right? So now this red cross, it just lies inside the light orange region. So now when we permute, we'll get some points which are in the blue region, some points which are in the red region, some points which are far away, because even by permuting one feature, we may basically land very far from the original point. So first thing is to make a lot of permutations of the point of interest, then kind of come up with a similarity score between those permutations and the original point of interest. So these are going to be your weights for the model that you build, right? Now this, as you can see, the contour here is completely non-linear, right? So it, say for example, this is the output of a very complex model. We will try and fit a surrogate simpler model. It could be linear, it could be any other simple model that we want to fit, and try and use the weights of that simple model to identify on or to explain only this local instance, right? So this, I mean, there's an option to select only top M features based on the complex model output. So we create n permutations, we score them using the model that we black box model that we've already built, right? Then we fit a simple model to the permuted data, which has weights depending on how far it is from the original instance. So the distance is basically kind of a similarity score. If we are going wrong, so our new data set becomes only these n permutations. Remember that we are just building one model for each point, correct? So it is only after I say that I want the local explanation for a particular instance, LIME will go and generate another, say, 1,000 points. It will take that data set and then try to fit a model only for the 1,000 points. And that model, we can perform badly on points which are far away from the point of interest, but we want to perform very well, or we want to have accurate predictions for points which are very close to the point of interest, right? So it is weighed by that similarity score. Now, For example, if we fit a linear model, then the weights themselves basically will be the explanation or the local explanation for that model, right? So that is the rough kind of workflow that Lime has. Now, the main takeaway is that we actually don't require any of the training data that was used while training or while building the model. So that is one advantage that I want to highlight, that Lime has even over SHAP, which we are going to basically see. So Lime doesn't require any data point from the training data to find local explanations, right? So that's a huge advantage. Like there could be cases in industry where you don't want to share the training data. You just have an API where you can hit the model and get a prediction. Then Lime can be a very, very good choice for model explanation, as opposed to maybe a better method, which we look at SHAP, right? So this is kind of the rough overview of Lime. Coming to the slide, like faults in Lime is, this is a like cryptic diagram, but if you can see that if the actual model output function kind of takes a drastic turn after a certain feature value, then depending on the permutations or the observations that we generated, we could either we could have any of the three lines that fit this local instance, right? So there are cases where we may go very wrong with line for these instances which lie in sudden change of the trend in the function, right? So I'll not go more, I guess, into depth of line because we still have to cover SHAP. But as I mentioned, the main takeaway is that it doesn't require the training data. So coming to SHAP, right? And I thought that just going through this math would be slightly beneficial because in many places, so this has been taken from an excellent article that I have also pasted the reference at the end. But let's try and just understand in the basics, like why SHAP is maybe a much better option than Line, correct? So SHAP comes out of concepts from game theory, and the game theory concept basically shapely values, which is the expected marginal contribution, right? So let's take this simple example that we see here, okay? And what we see here is basically the way this entire problem has been framed is, say that you are entering a competition and there are two people, right? C1 and C2. Now, if C1 enters the competition, or if player one enters the competition uh, by himself or herself, they earn 7,500 rupees or dollars, right? And C2 or player two, if they enter, they earn $5,000. Okay. And when both of them enter together, they earn $10,000, which could be, say, the first prize. And obviously, if none of them enter, then they won't win anything. Okay. Now, the question is that when they do enter the competition and they win, say, 10,000 rupees or dollars, how would you basically bifurcate or divide this amount between the two players? Now, if we look at this problem, I mean, many people would say that, okay, 7,500 they would have earned individually, 5,000 would be 5,000 the other player would have earned. So let's divide the 10,000 in the same ratio, right? But so let's just do that math quickly. So if I have 7,500 and 5,000, so this is summing up, right, to be 12,000 500. So this is 60% and this is 40%, right? Right, as we can see here. Now, if I had to divide the 10,000 when both of them were, then they would have got 6,000 and 4,000 rupees, right? But if we calculate the Shapley value, and once I think we calculate becomes more intuitive, it's not exactly 6,000 and 4,000 that each one should receive. You will see that the answer basically is that player one should receive 6,250 and player two should receive 3,750. Now, what is basically Shapley values? It basically sees that it only sees when you add to a current combination or a coalition, it's called, how much extra value are you bringing to the table, right? So there are only two possibilities here. There are, because it's just a two-player game, you can come by yourself, right? The player one could come by themselves and earn 7,500, correct? Or player one could join with player two and basically earn 10,000. Now, when player one comes with player two, he's basically adding an additional value of 5,000 because C2 would have anyways won 5,000 by themselves. Whereas when they come on their own, basically they get an incremental value of 7,500. So the total incremental value across all possible coalitions becomes 12,500. And if we take the average, we get this number called 6,250. Correct. Now, if we do the similar calculation for two could come by themselves on 5,000, or two could come after one, where they would earn 10,000, but the incremental value is only 2,500, right? And if we divide this by two, we get 3,750. So this is one kind of allocation that is possible. And there are basically good theoretical reasons why this allocation is fair. I'll just state the axioms later, but let's look at another example where we have three coalitions. Okay. Very similarly, just running through the example. If you see here, C1, C2, and C3, if C1 comes by themselves, they earn 5,000, C2 earns 5,000, C3 doesn't earn anything. And each of the coalitions, the kind of a lookup table has been provided to us. So C1, 2, 3, if they all three come together, they earn 10,000, right? Now, in order to calculate how much should C1 receive, all the possible ways that C1 can enter the combination are basically calculated, and the incremental value that it has brought to the table is calculated, right? So one can come after 2 and 3 have already entered, so it brings additional value of 5,000. It could come only after 2, when it basically gets an additional value of 2,500. Similarly, after 3, 7,500, and by themselves 5,000. Now we have these four values, but what is of interest is that if we now have to calculate the Shapley value or the fair allocation value, this 5,000 is multiplied by 1 by 3, 2,500 is multiplied by 1 by 6, 7,500 is multiplied by 1 by 6, and 5,000 multiplied by 1 by 3. Now the question is, why are there different weights for each of the possible coalition entries, right? Hence, this table, big table that you see on the right, is all the possible ways or the sequences in which one could have entered any kind of coalition, correct? So if you see, if one enters after 0, post that there could be two more ways, right, of the team being formed. So 2 could have entered after that, or 3 could have entered first and 2. Similarly, if 1 enters after 2, there is only just one way of basically forming the team, that is 3 enters post 1 enters. And then if already 2 and 3 have entered, still there is just one way, right? And again, if 3 and 2 have already entered, there is another way. So This is basically weighed by giving appropriate weightage as per the number of combinations or the number of combinations in which one could have entered that allocation, right? So if you see the formula, you basically get this big formula, and this part is nothing but this weight that we see here, 1/3, 1/6, 1/3 and 1/6. And this is the marginal contribution of player I to coalition S. Okay, so this is this lookup table of 5,000, 2,500, 700, 5,000 that we have calculated, right? Now, there are some theoretical reasons why this turns out to be or fair allocation. So I'm just listing them down. One is symmetry. So if two players are interchangeable and they make the same contributions to all coalitions, okay. And then there's obviously null player property, which is basically if player makes zero marginal contribution to all coin, then they get a null value. And main is the additivity, is that if we combine two games, then we can basically sum up the contribution for those two individual games for any of the player. So on these three axioms, the Shapley value is basically kind of derived from, and this turns out to be a fair and full allocation. That is, whatever the value is, 10,000, everything gets divided amongst each of the players. Now, in this context, this may seem very trivial, but if we apply it, or the way it has been applied in for feature importance, is that value of the game is basically the model prediction and the feature value are the players, right? So if we go back to the first example, then C12 is nothing but feature 1 and feature 2 combined gives, say, a prediction of 10,000. And here feature 1 by itself, or feature 1 equal to some value by itself, is contributing 7,500, and feature 2 by itself is contributing 5,000. Then how important is feature 1 and how important is feature 2 is exactly the problem that we are trying to solve, right? And this is done for every instance. So every instance is a game where we try and do a fair allocation of Shapley values, right? And just getting into a small subtlety, it is not the features, but the value of the features for a particular observation that play the game, right? So when I say feature 1, one instance would be, say, feature 1 equal to 10, feature 2 equal to 20, and the prediction is, say, 10,000, right? So the player becomes feature 1 equal to 10. When the value of feature 1 is equal to 10, what should be the allocation given to feature 1, right? So this is the way the Shapley value has basically been applied to the interpretable model. And SHAP is just one of the implementations. So Shapley value was there for a long time, but SHAP is one of the implementation of Shapley values, which one, it has a great set of visualizations to visualize the feature importance. And two is that it has a very optimized implementation for exclusively for tree-based methods, right? So though the entire Shapley value concept is model agnostic, but its most optimized implementation is used only for tree-based methods, right? So for other methods, there could be like a time trade-off, and that's where Lime maybe becomes better in some of the cases, because Lime could be much quicker and would give you a sense of the rank ordering of the feature importance, right? So I won't go into much depth into these graphs, but just to show that kernel SHAP is something that is model agnostic. So it can be used for all kinds of models, and tree SHAP is basically um, the optimized version of Shapley values that has been developed for tree-based methods. And that is the main feature of the SHAP package, right? So let's just have a quick look at the SHAP package. So here I can show you one example, quick example for Lime and SHAP, and then maybe move on to the cricket data set. So for Lime, there is a package called Lime itself in Python, uh, which we can use. So let me just run this notebook. Or maybe I'll just go through this notebook rather than running it. So this is another data set of shells. Basically, Avalon is kind of shells, and where we are trying to basically predict the age of the shells given certain features like length, diameter, height, right? So we fit a regressor, and here we are basically creating a Lime tabular explainer, right? And once the explainer is instantiated, like we can see here we basically mention how many features do we want to use, right? So if we go back to our slides, um, we do remember the step that there is an option of basically just selecting the best features for that local output, correct? uh, and then Lime kind of gives this kind of an explanation. So positive, negative would be just that which features have affected in a positive way and a negative way. It also, now here, this is a slightly important piece where you see that the right here means the actual model prediction is 12.6675, whereas the local prediction is 10.88, right? So this is what is different in SHAP. Here the local prediction is 10.88, so your weights, whatever linear model it has filled, or even say or it has built, or say a tree based model, it would add up only to 10.88 and not the complete 12.66. So there is, first of all, it may not be a fair allocation, but even the allocation is not full, like the entire value of the output is not allocated to all the features, right? Hence Lime is a suboptimal, or a very in some, it's actually a very special case of SHAP, right? If you actually we use a kernel SHAP with a linear model, we kind of get Lime interpretations. Okay, but just to go through this, so Lime basically will give you these feature importance, and it will also give you a small table of what the feature value was. Now, this is one small hack, and I will, this is also taken from another article, but I'll post this, post the GitHub link later on, is that SHAP has these nice plots. So first, just let me show you the SHAP plots, right? Or just maybe let me run the, yeah, let me run this. So let me just show you the visualizations available in SHAP. So this is an insurance data set. I'll just run through this quickly. So where we are trying to predict the price of the premium, like how much. This is a health insurance data set where whether the attributes like whether it's smoker or not, uh, what is the age, female or male, and then the BMI, and so what would be the eventual premium, right? That would be charged. So once we build the model, so the first plot that SHAP has is basically this bar plot showing how important each feature is. So in order to, now this is a global view, as I said, that even for local models, um, what it basically does is it takes the absolute SHAP value of each feature and it sums it up across all the instances. So any feature which has affected in a negative way or a big positive way would basically be all added up, and the largest value would be the most important feature. So here we can see that for health insurance, being a smoker or non-smoker seems to have the largest impact on the premium. Then comes the age, BMI, children, like very intuitive, right? But it is quantifying the importance in an appropriate way. So that is something to just keep in mind. Then it has these nice waterfall plots. Uh, these waterfall plots, though, are not available for the tree methods. They are only available for the general explainer, but it kind of nicely shows uh, how each feature has contributed and what the feature values are too. And you would see this, that it always gives the prediction or the contribution from the mean value of the entire data set. So that is because when we go, like if we go back, right, to this slide, the value of the coalition of say two features is the incremental value over the average. Okay, it is not the final model output, because if we didn't have any feature, the easiest thing that we could do is predict the average, right? If you're optimizing the mean square error, we just predict the average of all the target values. So that is like the base, that is C0 with nothing, no feature, right? So with all features combined, the value of the coalition becomes the incremental prediction that it has done. It could be in a positive or a negative way. Hence, when the SHAP plots are plotted, it always keeps the expected value as the reference and then gives how much incremental differences each feature got into the output. So here, if I had to draw a parallel with the game theory concepts, so the value of the coalition was it would have been 26726 minus 12813, whatever that difference is. And the players were basically smoker equal to 1, age equal to 62, BMI equal to 26.29. So there are feature values are the players, and basically the incremental value becomes the value of the coalition. Then it has scatter plots that you can plot to see the how the SHAP value varies with the feature value. Then similarly, there is also something called a force plot, which is very similar to the waterfall plot. Just like more compact way, if you're kind of seeing 2, 3 explanations. So here you can see that we are just seeing one instance, right? And seeing how a feature has contributed in a particular way. Then there is something called the decision plot, where we can take a slice of the input data and see the decision making path. So these are all variations of just the same SHAP values that have been obtained, but different ways of viewing them, right? And finally is the bee swarm plot, which is one of the most common plots. So just to explain this in more detail, this would be arranged by the order that we saw in the first bar plot. The most important feature on the top, second most comes age. The coloring is based on the feature value. So what this says is when smoker is high, now smoker is actually a binary variable, we know that. So if you see when smoker is 1, smoker is equal to 1, the SHAP values are usually on the positive side. And when smoker is equal to 0, the SHAP values are on the negative side. So the premium becomes lesser if you are a non-smoker, right? So similarly with age, but you can see that for though smoker is equal to 1, for different instances, it has different SHAP allocations. The SHAP allocations are not the same because it would depend on how other features have interacted for that particular instance. So though they are all high, they are basically they're different and will add up to the final predicted value. That is the additive nature of SHAP explanations. So yeah, so this kind of gives you the different plots. Just to once again go through it, we have the bar plot for the global feature importance. Then we have the waterfall plot for looking at a local importance. Similarly, we have the force plot for looking at one local explanation. Then we have the decision plot where we can choose to select as many instances as we want and plot each of the decision functions. So it's kind of an ice plot that we had seen right earlier, where we see the curve for each instance. Though this is on all the features, so it's not same, but it's the local version of the global ice plots. And the bee swarm plot, which kind of gives us the sense of correlation of how the feature correlates with the SHAP value, right? Yeah, so these are the plots in SHAP. So let me just run you through one final notebook and one real data set, which kind of we created. So let's say that we are analyzing a cricketing data set. So I've picked this data set from, it's available, I think, on Kaggle. Yeah, it's available on Kaggle. So it's basically the IPL ball by ball data set and the match data sets from 2008 to 2020. So it's a very just a simple exercise that I've tried, but where we are trying to just build a normal win and score predictor. Okay. So for in the interest of time, I'll just brush over the pre-processing. So the ball by ball data, as you can see, contains a match ID, the exact ball number, and which batsmen were on strike, whether there was a dismissal or not, right? And the team. And the match IDs are who won the toss, who was the winner, what was the result, right? So I've just created few additional columns here where, because the ball number is just in terms of over and ball, I've just created another index or a rank kind of thing just to get the ball number, whether it was the 100th ball of the first innings or the 90th ball. And then cumulative runs and cumulative wickets is something that I've calculated. So the idea is that we want the state vector at every ball, and if that team had won, we would basically apply label 1. If the team had lost, we would basically apply label 0, right? And just bin a win predictor. It may not be the best way to do it, but just for just checking the feature importance as a feature importance exercise, just wanted to check what comes out. So at the end of all this merging, we created 4 data sets, right? So you can see here, one is for innings 1. The win predictor, we need to segregate innings 1 and innings 2, because in innings 1, we are not chasing a target, right? So the target variable, we can combine them, but just to understand the models better, the target variable would not be present for inning 1, whereas the target variable would be present for innings 2, and that would kind of dictate how the players play the innings 2, right? So even though they could have accelerated, they just may choose to pace out their innings. So there will be 2 models for the win predictor and 1 model for the score predictor only for innings 1, because innings 2 you're chasing a target, doesn't maybe make much sense of having a score predictor. So we create these 4 data sets, and we first build a win predictor for innings 1, right? So here I've tried to build just 2 models, one XGBoost classifier and the gradient boosting classifier. So both of them give a very modest AUC of around 67. Okay. And first, let's see the partial dependence plot. So I just want to know how each of the features that we have put in. So just let me pull out which features we have used. Yeah. So for innings one win predictor, we have used cumulative runs. So basically, how many runs have been scored till a particular stage. What is the ball number? So say if it is the 12th over, then 84, then 72. Then how many wickets have been lost, and whether the team won the toss or lost the toss. Okay, just wanted to add that variable and see. So these are the four features that we are using to basically build a win predictor. And now what we want to know is how do these features, how does the probability of winning vary with these features, right? So let's see of the cumulative runs. So on an average, the orange line that we can see, it kind of indicates that as the cumulative runs basically increase, the partial dependence or the model output, right, the probability of winning kind of keeps increasing, right, which is fair. But you can see that there is quite a large variation from the IC plots, that there are instances where the first inning score is not basically telling us a lot about the probability of winning because the variation is so high, correct? So even if you have scored around 170 or 180, there are many instances where the team would have lost, right? Next is the ball number. Now this is a very weird one. Ideally, if I just put in the ball number, I mean, unless you give me some other variable, it would be very hard to tell, right? What basically is the effect of ball number. I mean, ball number by itself shouldn't be having any effect. And this is where maybe your PDP plot kind of fails, because it still gives us some variation, because it treats all the features as independent, correct? Then cumulative wickets is maybe more the wickets you start losing on an average, you can see that your probability of win decreases the more the wickets you have lost, because that means at some stage in the match you would have maybe slowed down your run rate. And surprisingly, or I mean, good for game, that the toss doesn't seem to have any impact on the, or much impact on the winning percentage, right? Now this ball number is basically, many of these features we want to look at the joint distribution. Like if I say the ball number and the runs scored, or give a particular stage, then what would be the probability of winning, or how does my probability of winning vary? So we've drawn two joint partial dependence plots. So here you can see one is the ball number and the cumulative runs, and the other is the ball number and the cumulative wickets, right? So there are certain interesting patterns here. So if you see, at least the first is the cumulative runs and the ball number, right? So as the ball number, or we can see here, is that as the ball number increases, it just depends on what your cumulative runs is basically, which would dictate your probability of win. So if your runs is higher, your probability of win would be higher, right? So you see that ball number doesn't have an effect for much part of the entire graph, correct? And the entire thing kind of just kicks at the middle of the ball number, because that's when it is kind of correlated with the cumulative runs too. In terms of cumulative wickets, you can see that if you, at the end of the innings, you still have more wickets left, then your probability of winning is kind of higher, because if you have more wickets left means you would have gone full throttle for the entire innings and would have scored more runs, right? And hence your probability of win would be higher. Hence here you would see that most of the concentration is around here, whereas in cumulative runs is around the top part, right? But in both the cases, this green patch that we see here is that the ball number has practically no effect on the winning percentage for quite some time. Correct. And it shouldn't basically have, doesn't make much sense. Now, similarly for innings two, when so as I said, the ROC for the innings one model was around 67. When we build it for innings two, um, okay, before that, the if we see the global importance of the features, we see that cumulative runs. So basically, higher the run scored, better is the chance. Ball number could be just that more the balls played, and cumulative wickets. But this is another problem with SHAP is that if we have two correlated features, it would kind of give equal importance to both of them. Okay, so there are other ways on SHAP that we can build on and basically try and find the set of correlated features. But you can see here that ball number actually doesn't make much sense here, but it still gets as much importance as a cumulative wickets or a cumulative run somewhere in the middle, right? And these are the same plots that we've drawn for one particular instance explanation. Now, a similar model for innings two basically gives us an ROC of around 91 because we have the target in sight, and I think within 2 or 3 overs, we can basically kind of know where the match is going, right? So it gives us a much higher accuracy. I'll just skip to the feature importance part. So here target runs takes the maximum importance as expected, because that's what would govern the winning percentage, and then the runs scored by the opponent or the team batting, post which it's wickets in hand. And again, ball number turns out to be a slightly spurious output, which we kind of need to address, right? So here, yeah, and finally, the score predictor is just for the first innings. We try and predict the score. And if you look at the partial dependence plots here, so here I've just drawn the partial dependence plots and not the ICE. It can be controlled by a parameter. So here, if we just plot average, it will just plot the partial dependence plot. So these are partial dependence plots from scikit-learn. And if we see, it has very similar behavior as the win predictor, your cumulative runs. So as your runs keep increasing, your predicted target would increase, cumulative wickets. And same between cumulative wickets and cumulative runs, it shows that if you have higher runs and lesser wickets, then yeah, the target that basically would be target set would be higher, and the toss has still no impact, right? I mean, on the target set. And then this is the final PDP plot from just between the ball number and cumulative runs, right? So similar to, like, if you basically have more runs scored, then you would have more target, right, scored. Here you have a 64. So this was one kind of example, the real data set, just to process the data, find out explanation, and read the insights, right? So just kind of concluding what we started. So I'll try and like end the talk now here, but just before that, I just wanted to mention there are more methods which answer different kind of questions. So we have looked majorly at two questions that are answered by interpretable models. One is, what does each feature contribute to the model prediction? So that is the local, those are the local methods. And the global methods is how does model prediction vary with respect to features of interest, right? And there is another question. This is like a very interesting method called counterfactuals, but like won't be able to cover it in detail. So this basically tells us that what minimal change to features is required to reclassify the current prediction, right? So this actually could be used even in the cricketing example, where if you are given a situation and if the team is say losing, if I ask a question that what should have been the score, or should they have lost a wicket or two less or scored 10-20 runs more so that the team would have been in a winning position, how do you quantify that, right? So cricket may not be an example which is of real value, but say in terms of loan prediction, right? So if you have a certain instance and you want to find out that what is the least change that has to be done to that instance so that the loan gets approved, then you basically want an very simple answer saying that okay, you may need to keep a good credit score or whatever, right? So in those areas, I think counterfactual explanations are very helpful. There are it's not a very easy, there's no easy way to calculate them, so there are a bunch of algorithms. Two main algorithms that are used, one is the genetic algorithm approach, and currently even reinforcement learning is basically used to calculate counterfactual explanations. So very rough output is like what you see here, right? If basically what so if you see the last line, the prediction is that the first column, which is the input, they earn less than 50 say dollars or $50,000 a year. What would they require to earn greater than $50,000 a year, right? So the counterfactual that the algorithm gave was that you require a higher education, and you also require to change your occupation to a white collar job, so on and so forth, right? So it gives you a sense of the least change that one needs to do to get on to the other side of the prediction, right? And you can also give like a value for the prediction, like you can say that like if it's a binary classifier, so if currently the team is at 40% win probability, what should the team do to just get to 70%, right? So yeah, it's more useful in areas in finance, I guess. So to conclude and to summarize everything, so this is just a simple cheat sheet that I've drawn. So there are the center, you have explainable AI, and there are a host of methods. But if you had to just go back and start implementing, right? So one is just ask like, what do you want to analyze? So do you want to analyze the global variation of the model with respect to the features? Then you have two options. One is the PDP plus ice plots, and as the accumulated local explanations, right? So one should use accumulated local explanations when you're sure that they are highly correlated features. If they aren't, if you feel the features are independent and there are many categorical features, you can go with the PDP plus ice plot, right? Similarly, if you want to get local explanations for each of your instances, then if you have a tree-based models, I think and anytime the SHAP package would be a better option. Also, like because it has fair attribution. And remember that SHAP, even if you have categorical variables, would give you a real number allocation. So there are many things which like I have not covered here, but you can do on top of the SHAP output. And for non-tree based models, and I said like in cases where you don't want to share your data, or the data like for some privacy concerns, even if it's a non-tree based model, then Lime could be a very quick solution to at least get an understanding of the ranking of the features. And lastly, it's the counterfactuals, which I couldn't show the example, but if you want to answer the question that what minimal change needs to be done to the features to reclassify the current prediction, then we can use the counterfactuals approach, right? So that's the summary. I think it's like a very broad overview. Hope it was helpful to you. Yeah. So I've pasted the reference and further reading. I'll kind of uh, share all the code that I showed today so that you all can run it.
Okay, thanks a lot, Shiladit. Now, by the time you take some questions from the Q&A section, I would like to request the attendees of this e-meeting to please fill out the poll in the section, which is about the feedback. That helps us to conduct these sessions regularly. Now, Shiladit, over to you. You can take a few questions from the Q&A section, keeping in mind the time constraint as well. Already we are running short of time. So yeah, we can have a look at the Q&A section first.
Yeah, sure. The key difference between
I guess most of the questions you have covered in the session, but you can take the ones which you haven't covered or the doubts.
So is it computationally expensive to calculate partial dependence plots? Uh, e- I think like yes, if you compare it to ALE, they are more computationally expensive. So you can vary the parameter of the grid size, which I showed, like which has say 100 points. You can even have lesser number of points because the global methods are just giving you a sense of the variation, right? As I said, like SHAP, where you are guaranteed of fair allocation, you can actually do some kind of clustering on top of SHAP values. So say there are two features which are getting attributed the same SHAP value in almost each of the instances, right? So then those two features become kind of similar. So you can do kind of a hierarchical clustering on top of the SHAP values and see which features are correlated. So for your partial dependence plot, which is just trying to give you a sense of what the model is doing, you can try and make it computationally less expensive by varying these parameters. But ALE plots are lesser computationally expensive than PDB plots. How is y11, y12, y13 value calculated? So that's the output of the model. So for those instances, even for the perturbed instances, you are basically going to again do a forward pass or run the predict function of the model, right? So here you're trying to approximate your model output. So it may not be the real truth. You're trying to understand what your model is predicting. So if you have a wrong model, it's going to show a wrong explanation too, right? It is not the ground truth. You're as good as your model, right? So partial dependence means partial y to grade fg at every point in feature have to grade. Yeah, so we have to basically bin one feature, get those values and apply it for all the possible instances of the other features, which is basically your data set kind of provides you that distribution. So if you have 10 points, if you want to basically chart out 10 points for a feature, and if your data size set is say 100, then that intermediate data size would be 100 into 10 just to calculate the PDP for one of the features. Then you'll have to do it basically for each of the features. So it won't scale well if the number of features is very large. Feature importance can be, so depending on like how independent the features are, but that's a huge if. Hence PDP plots alone may not be the best to tell about feature importance. It more highlights the variation of the features at different intervals of the feature variation of the model with different intervals of the feature values, which say a SHAP is not providing you in one visualization. But even SHAP has its own dependence plot. So the local explanation methods can always be aggregated to get a global view. Yes, I'll share the notebooks. Uh, yes, SHAP is very computationally intensive as compared to LIME. Hence, the highlight of the SHAP package is, I mean, shapely values. The idea of shapely values was proposed much earlier, but the implementation of SHAP lies in the beauty of its optimization for tree-based methods. Hence, like look up the tree SHAP explainer. That will be way fast than say a line, because it's able to compute the value of the coalitions while building the model, basically. So the value of the coalitions, like in our dummy example, we had to basically list down the value of the coalitions. The value of the coalition are nothing but the model output, right? So if we had to actually find the value of each coalition, we would have had to build those many models. So I think I didn't really show you how many, like it's basically exponential, right? So if you have three features, you'll have the entire power set. So 2 raised to 3, 8 models you'll have to build. Similarly, if imagine if you have 100 features, it's going to just blow out of proportion. So hence, it's impossible to calculate the exact SHAP values, but for tree methods, they have optimized it. For classification, the same plots can be used. The only thing I didn't highlight is that for classification, what it basically, so the additive property by default, what SHAP gives will hold for the log odds and not for the probability. So it is not like whatever output we get from SHAP. So SHAP output will be log odds, and that would be additive in nature. Like how we saw for regression, like say for the score predictor, if I add up each of the SHAP values, I'll get the final score. But for probability, if I add up the SHAP values, I'll not get the final probability. I will get the final log odds. And if there is now a parameter where we can get even the interpretation in terms of probability, but there are a couple of changes that need to be made, and not all plots would be supported with that. So is the PDP plot like variance inflation factor? Not exactly, because it's not like a single number. It kind of is giving you an average model prediction. It would, I mean, it's trying to give you an average conditional expectation, but I won't say it's exactly like a VIF. PCA, not sure about dimensionality reduction, but do we need to standardize our features before putting it into SHAP explanations? No, there's no requirement of standardizing the features. Yeah, I think those are about it, the questions. Yeah.
Okay, thanks a lot, Shiladit. On the behalf of the complete Analytics Vidya team, I would like to thank you for your time and for delivering such a wonderful session. I'm sure these guys or the audience would find it insightful, and hopefully we can conduct more sessions with you in future. Many of you were asking about the LinkedIn profile of Shiladit, so I pasted the link in the chat box. So I hope the attendees, you guys have filled the feedback poll. If not, I request you again to please fill it in the poll section, as these feedbacks help us to conduct more of these sessions regularly. And if any of you want to conduct a webinar through a data hour, you can contact us at datahour@analyticsvidya.com. Also, I got a few questions in the chat box regarding the recording of this session. So I'll be pasting the YouTube link of the Analytics Vidya playlist in the chat box. You can go and have a look over the recording of the session as well. So we have a lot of upcoming data sessions lined up. You can check that in through our DataHour website. I'll be pasting the link in the chat box as usual. So yeah, until then, we'll meet in the next data session. Bye bye and keep learning. Thanks a lot, Shiladitya.
Thanks a lot. Thanks a lot. Bye.
Thanks for